All right, ladies and gentlemen, welcome back. So today we're going to put together all of this information that we've been learning about what a cladogram is, how to read it, and actually construct one. If you can build one, you can read one. So let's take a couple of points here. One of the things that we need to do when we're creating a cladogram or phylogenetic tree is to create a comparison table. And a comparison table really is just comparing the species that you're looking for and who has the characteristics that you have decided to include as a means of determining their evolutionary relationships. Um, in addition to those species, you're also going to create or include what we call an outgroup. And an outgroup is a species that you're going to utilize who has none of the characteristics that you're comparing. So they will essentially be blank. They will be the first one on your cladogram because they are the most distantly related ancestor to all the other organisms in that cladogram, in that grouping that you're looking at. When you then create the comparison table, they typically use ones and zeros or pluses and minuses, or you may see X's and blank boxes. We'll practice a bunch of different options just so you get to see them. But essentially what we're looking at is if it has a 1 or a plus sign, or if we use that X scenario, then they have that characteristic. If we use a 0, a negative, or just a blank box, then they don't. And then we can use that set of data to then build the tree. So let's look at what this looks like and build a comparison table together. So here I have a group of organisms, a hagfish, a shark, a ray-finned fish, amphibians, primates, rodents, crocodiles, and birds. And to build this particular cladogram, we're going to use the derived characters across the top. So a vertebrate, bony skeleton, 4 limbs, amniotic egg, hair, opposable thumbs, eggs with shells, and feathers. And if you look, we're including that hagfish because that hagfish has none of the characteristics that we're looking for. And so this is our outgroup. So when we go to actually start building the cladogram, that hagfish is going to be the one that branches off at the base of the tree because they are the oldest presumable relative to everybody else. Okay, so here's what I want you to do. I'm going to ask you to stop the video here and fill out the table. Go to Google if you need some help, but try to complete the table with those ones and those zeros. Remember, 1 means they have it, 0 means they don't. When you get that comparison table completed, come back to the video and let's move forward. All right, guys, so welcome back. So you should have at this point filled out your comparison table, and it should look something like this. If it doesn't, pause the video here, double check your answers, and make sure that yours matches mine. This is going to be the data that we're going to use now to build out our cladogram. Okay, so let's actually start building this cladogram now. So remember we said that that hagfish, right, this is my outgroup because it doesn't contain any of the things in common. Okay, and so that means when I come down here to build that tree, that hagfish is going to be the first one. Okay, now the question becomes, where does everybody else go? And so there's a couple of ways that you can look at this. You can either go across the rows or down the columns, but we want to count up how many things are in common. So I'm going to go across the rows. So I'm going to count how many ones there are. So if I take a look at that shark, he's got just 1. Okay. Ray-finned fish has 2. My amphibians have 3. My primates have 1, 2, 3, 4, 5, and 6. My rodents have 1, 2, 3, 4, and 5. My crocodiles have 1, 2, 3, 4, and also 5. And then my birds have 1, 2, 3, 4, 5, and 6. Okay, so now these numbers tell me something a little bit about where these organisms are going to go. Your lower numbers will end up down here towards the base of the tree. Your higher numbers will end up closer to the top. So let's take these one at a time. And I also like to cross things off as I do them. So we've already got the hagfish in there, so I'm going to take him off the list so I know that I took care of that. So the next thing I want to look at then is who has the fewest number of characteristics. And that looks like it's our shark. And if I go down that characteristic that that shark has that the hagfish doesn't, that's that vertebrate, and so does everybody else. So that means that that shark is going to be the next one to show up here on my tree. Okay, so I'm going to cross off that shark. Now, in the process of doing this, we should also be including our derived characters and where they show up. So that vertebrate was that distinguishing feature between the hagfish and the shark. Everybody else other than that hagfish has that vertebrate. So that means that that's going to come down here as a hash mark here. Okay, and so now I can take that off the list as well. Okay, so who comes next? Well, I start looking down my list. My rayfin fish comes next. It had a vertebrate, so we've already taken care of that. It now also has a bony skeleton, and again, so does everybody else. So let's go ahead and add that rayfin shark, excuse me, that rayfin fish. And let's include that bony skeleton. Okay, so now I can take those off the list. Okay, amphibians come next. They've got everything but the 4 limbs. Everybody else below them does as well. So we can add those amphibians. And those 4 limbs. Okay. All right. Now things get a little more complicated because I have 2 5s and 2 6s. So let's go ahead and take a look at those 2 5s. So that includes our rodents and our crocodiles. If I look, they both have those skeletons. They both have those skeletons, the limbs. They also have the amniotic egg, which so does everybody else who's left, by the way. So that tells me that that amniotic egg is the next derived characteristic. So let's go ahead and add that on there. And I can take that off the list. Okay, so that then leaves those rodents and those crocodiles. And if I look, these guys have rodents having hair but nothing else. Crocodiles have the egg but nothing else. So that's going to tell me that these guys are actually going to branch off of each other. So I'm going to put them on here, and let's put those crocodiles and those rodents. Okay. So the rodents and the crocodiles are on there. That also tells me that those primates and birds have to come up top here. Okay, so now all of my species are taken care of. What about the traits that I have left? Well, I've got hair, opposable thumbs, eggs with shells, and feathers. If I look down those crocodiles, all right, well, they have eggs with shells, but the rodents don't. So that means it's going to be something that's unique to them. Okay, but the birds also have it, which means that this is something that actually showed up more than once. It's unusual for that to occur, but it's not impossible. And given the data that we have, that seems to be the best fit. So we're going to take that one off the list, and that one's going to be something that showed up twice. All right, what else do I have? Well, I have hair. Same deal. It shows up in two separate lineages. So we're going to put them on there separately. And again, not what we would typically expect, but not impossible either. And so given the data, that's our best scenario. That's our best hypothesis as to how this came about. Okay, now I've got opposable thumbs, which is unique only to those primates. If I look at who's left, that's something that's unique to them. So that's also going to go on their line as well and nobody else's. I'm just going to give myself an arrow here to give me some space. Okay, so that takes care of that. And then I'm also left with those feathers, which again is unique to the birds and nobody else. So that means that's also on their line, independent of everything. All right, so now I've taken care of all the species, all the characteristics, and this is the cladogram that I'm left with. Now, when we talk about evolutionary biologists creating these cladograms, they can use that information in physical data like we just created, but we can also include information based on shared different amino acids, in proteins, in DNA sequences, in RNA sequences, because remember that molecular data, that flow of information goes from DNA to RNA to amino acids in our cells. So the instructions to make the amino acid sequence, aka the proteins, are kept in your DNA and your nucleus, but in order to get that set of instructions out to your cytoplasm, to the ribosomes where we build those amino acids, that RNA molecule is the intermediary. So I can use any one of these sequences as a way to look at comparisons. The more things they have in common, the more recent their common ancestor, the more differences, the longer back they diverged. So I can utilize this molecular sequence data independently of that morphological data, those physical traits that we just looked at, or I can use them in combination with each other. And realistically, the more sets of data that you have that come up with the same organization for those cladograms, the more support you have for that hypothesis and the more confident you are that that's how it works. So if I were to come back and use this physical data and then also create a table using molecular data, creating a cladogram with molecular data, and they came up with the same order, then I'm way more confident in the order of the evolutionary relationships here than if I just used one or the other by itself. So let's try this one. So I've got 5 new species of bacteria that were discovered in Antarctic ice core samples. The proteins were determined for the new species. The table shows the number of nucleotide differences between those species. And then we're asked which of the following phylogenetic trees is most consistent with the data. So we're looking here at this table, right? And they're comparing each other. So here's species 1 to species 1. They don't give me any data because I'm comparing the same species to itself, which would essentially mean that this is just another way to say that there's 0 differences. Does that make sense? Okay. If I compare species 1 to species 2, there are 3 differences. Species 1 to species 3, there's 19 differences in their sequence, so on and so forth. Now, we don't have any data down here because you're essentially saying the same thing. It's duplicate data, so 2 to 1 is the same as 1 to 2. So this would just be another 3. It's redundant, and so they don't bother filling in the bottom of that table. You have enough data here. Okay. So first thing I want to look for is which 2 species have to be furthest away from each other on the tree, and then I can start narrowing down my choices. So the further away from each other they are, what does that mean in terms of will they have a very high number of differences or a very low number of differences? I'm going to give you the opportunity to try and come up with an answer yourself. Okay, so now that you've made an attempt, let's take a look at this together. So if I look, the biggest number of differences in the table is that 27, right? So that means species 5 is most unlike pretty much everybody else. So that means that species 5 has to be the furthest away. So it's probably at one end or the other. What does that eliminates letter A? We've eliminated choice A because 5 is too close to everybody there. And if I take a look at B, it's kind of the same thing. It's too close to everything else being sandwiched in the middle. So that now brings me down to C or D. So typically what I do now is look at the exact opposite. Who has the closest number of sequences? Who has the fewest number of differences? And if I look at that, 3 and 4 have the closest, so that's 1 and 3. Now I come down here, and that means they've got to be close together. Well, that doesn't really help me because they are essentially next to each other in both instances. So let's go to the next closest, and that gives me species 2 to 3. So that means 1 and 2 should be really close together. Again, doesn't quite help, so let's keep working through it. If I look at 3 and 4, they have the same number of differences to 1 and 2. What does that tell me? Well, that tells me that these guys have to be on the same branch together as opposed to being branching off of each other. So what does that do? That eliminates letter D because they're next to each other as opposed to directly connected. And so letter C is the best choice given the data that we're presented with.